Hello students, let us solve some problems on Fourier transform. First problem is determine the Fourier transform of the unit impulse function, where unit impulse is x of t is equal to delta t. Delta t is nothing but this signal exists at 0, whose amplitude is here. We see the amplitude is 1. Draw its spectrum. Now we know the formula x of j omega is integral minus infinity plus infinity x of t e raised to minus j omega t dt. So let us take this equation. In this equation, so let us substitute x of t. X of t is nothing but delta t e raised to minus j omega t dt. But we know that delta t is 1 only at t equal to 0. Therefore, substitute t equal to 0 in the above integral using the shifting property. Therefore, substituting t equal to 0 in this equation, e raised to minus 0, that is nothing but 1. Therefore, x of j omega is 1 in the entire range of omega from minus infinity to plus infinity. Now, next problem, find the Fourier transform of the signum function. Signum is Sgn of t, and draw the magnitude and spectrum. So let us see what is a signum function. Signum function is nothing but it is plus 1 for t greater than 0. Therefore, it is plus 1 for t greater than 0 and minus 1 for t less than 0. This is what is the signal. So, in order to solve this one, we will differentiate this signal x of. So, differentiating x of t, that is nothing but signum of t with respect to t, we get x of d by dt of x of t is 2 times of delta, because if you see here this is a constant signal, therefore the integration is 0. Here also it is 0, but at t equal to 0, it is changing from minus infinity to plus infinity. Since it is increasing, it is plus, and how much it is increasing from minus 1 to plus 1, therefore 2 times of delta t. Now applying Fourier transform on both sides, we get d by dt, you will get j omega x of j omega 2 times of delta t. Fourier transform is 2 because delta t Fourier transform is 1. Now getting this j omega here, x of j omega is 2 by j omega. Therefore, x of j omega is 2. Modulus of this one is 2 by omega, whereas angle of j omega is minus pi by 2 and plus pi by 2. So substitute here and just see here. If you see, if I substitute j equal to, for greater than 0, it is minus pi by 2. For greater than 0, because 2 by j omega get multiply and divided by j, you get 2j minus omega. So if I substitute for omega greater than 0, here it is pi by 2. Here it is of like 0, x plus I by. So tan inverse y by x. Therefore, tan inverse something by 0 is infinity. Therefore, it is minus pi by 2 because of this one. Therefore, so for omega greater than less than 0, it is plus pi by 2. So now coming to the sketching of the magnitude spectrum. For just substitute at omega equal to 0, it is infinity, therefore it is coming from infinity. For omega greater than 0, it will be decreasing this side. For omega less than 0, it will be going this side. Now for omega greater than 0, it is minus pi by 2. For omega less than 0, it is plus pi by 2. Find the Fourier transform of a unit steps function. We have seen the unit impulse. Now this is unit step signal, which is given as x of t is equal to u of t. Signum function, whatever the signum function is there, we can express as this 2 times of u of t minus 1. So this signal, whatever is the signum function is there, that in terms of u of t you can express 2 times u of t minus 1. You can just substitute and you will get this signal. U of t is equal to, from this equation rearrange the terms, u of t is equal to 1 by 2 plus 1 by 2 signum of t. Now taking the Fourier transform of this equation, we get Fourier transform of u of t is, that is what we have to find, that is x of j omega is 1 by 2 Fourier transform is 1 by 2 constant. 1 Fourier transform is 2 pi omega delta of omega plus 1 by 2 signum function. Already we have seen the see the Fourier transform. This is, we can consider as a standard. Instead of solving everywhere signum function, you can remember this one, 2 by j omega. Therefore, taking here 2 to get cancelled, here also 2 to get cancelled, pi of omega or delta omega plus 1 by j omega. Now for the rectangular pulse shown figure, this is the rectangular pulse whose for the rectangular pulse shown in the figure, draw the spectrum. Here, this is a rectangular pulse where it exists from minus t to plus t, whose amplitude is 1. Now, so let us write the x of t for definition. Minus 1 to plus 1, it is 1. Otherwise, it is 0. So x of j omega is minus infinity to plus infinity e raised to minus j omega dt. We know that only from minus t to 2 it is 1, otherwise it is 0. Therefore, limits will change from minus t to plus t. So integrating this one, e for e raised to minus j omega t by minus j omega t in minus t to plus t, substituting the limits and writing in the form of 2 sine omega t by omega. Therefore, now, in order to get the value of x of j omega at 0, that is nothing but sine 0 by 0. So, therefore, it is of the form 0 by 0 using the L'Hospital's rule, that is nothing but differentiate the numerator and denominator. So, differentiating the numerator, you get cos omega t into t. Therefore, 2 times cos omega t into t will be there, right? Therefore, substituting limit, and on the denominator, omega differentiation with omega is 1. Therefore, when omega equal to 0, cos of 0 it is 1. Therefore, it is 2t. Therefore, at omega equal to 0 it is 2t, and the signal will be something like this, sinusoidal and increasing. Now let us see the another problem for the signal x of t shown below. This is what is the signal. We have to find the Fourier transform of this one, x of t, this x of j omega. Therefore, writing the definition, from minus 2 to 0 it is 1, from 0 to 2 it is minus 1. Therefore, x of j omega e raised to minus j omega t, x of t e raised to minus j omega t dt. Now, splitting this is from minus 2 to 0, it is plus 1. From 0 to 2, it is minus 1. So, substituting here and taking the integration, we get this 2. Rearranging the terms and writing, we get minus 2 by j omega plus 2 cos or 2 omega by j omega. So, we can take 2 by j omega common and write this equation. Compute the Fourier transform of the signal x of t is equal to 1 plus cos pi t, where mod of t is less than or equal to 1, 0 for t mod of t greater than 1. Therefore, x of j omega is minus infinity plus infinity x of t e raised to minus j omega t dt. Therefore, we know that from minus 1 to plus 1 it is this signal. Substitute here and split. So, multiply this e raised to minus j omega into this term 1 and also cos pi. Therefore, multiplying here, we get here minus 1 to plus 1 e raised to minus j omega, and writing this cos as e raised to minus I t plus I theta plus e raised to I minus I theta by 2 e into e raised to minus j omega t dt. Splitting all these terms and taking this pi and in these terms t and j omega common and integrating, we get 2 by sine omega by omega, sine omega by pi minus omega, sine omega by pi plus omega. Now let us see the next problem. Determine the time domain signal corresponding to Fourier transform. So here the Fourier transform is given. You have to find the its equivalent x of j omega equal to cos omega by 2 plus j sine omega by 2 for mod omega less than pi. Now we know that here it is from minus pi to plus pi. So here this is the formula, x of t is equal to 1 by 2 pi integral minus infinity to plus infinity x of j omega e raised to j omega t d omega. Here cos omega by 2 plus. So this is nothing but e raised to, this is of form e raised to I theta. This is cos theta plus I sin theta. That is nothing but cis theta. So substituting here and simplifying this, we get 1 by 2 pi minus pi to pi e raised to j omega into 1 plus 1 by 2 plus t d omega. So substituting this one and simplifying this, you get cos pi t by pi plus t by 2. So substitute the both the limits, take out this, you can take common and you can write this equation. Because you can write this one by j omega, substitute the minus pi and plus pi limits, you get this one. Using the partial fractions expansion, determine the inverse Fourier transform x of j omega 5 plus j omega plus 2 by. Now splitting this one denominator as if its roots and writing as the factors, j omega plus 3 into j omega plus 2. Now taking the partial fractions, the x of j omega is 3 by j omega plus 3, 2 plus 2 by j omega plus 2. Now taking the inverse Fourier transform, we get x of t is equal to 3 into e raised to minus 3t u of t plus e raised 2 times of e raised to minus 2t u of t. So x of t is equal to 3 times e raised to minus 3t plus 2 times e raised to minus 2t u of t. Find the inverse Fourier transform of x of j omega is equal to minus j omega by j omega whole square plus 3 times j omega plus 2. Let us see this problem. X of j omega is equal to minus j omega by j omega plus 1 into j omega plus 2. So by partial fraction expansion, just apply the partial fractions and expand. Taking the inverse Fourier transform, you get x of t is equal to e raised to minus t u of t minus 2 times of e raised to minus 2t u of t. Therefore, this is the expression for the Fourier transform.